Hello and welcome to Friday's edition of Cracking the Cryptic, where today we're going to take a look at the puzzle on the screen, which is called Prickly Pear, and it's by Samantha Mukherjee. Now, Samantha's appeared on the channel quite a few times before, always with puzzles that I've really admired, actually, because they always have a real elegance. They're not normally brutally difficult. I don't know how hard this one is, so I'm hoping it'll be about in his normal wheelhouse. We'll have to see. I'll read the rules out in just a second. A couple of things to mention first. We got something brilliant sent to us yesterday by Stephen Chrisomalis. Stephen, I hope I'm saying your surname correctly, but let me show you what it was. I tweeted about it yesterday, so some of you will have seen this already. But it's a short story called The Devil Went Down to Surrey. I mean, actually, receiving this yesterday, I wish I'd seen it before I recorded the Phistomefel video that appeared yesterday on the channel, because it's a short story about somebody called Maverick meeting the devil somewhere down in Surrey, which is where I live. And I laughed out loud many times when reading this. This is really, really cool. If you're in any way familiar with some of the things that go on Cracking the Cryptic, it will mean a lot to you, this, I think. And it's very clever because it's got 3 puzzles built into the story. And if you solve the puzzles, you get one ending. If you don't solve the puzzles, you get a different ending. So, yeah, what I'll do is I will link this under the video. The puzzles are all very approachable, very interesting, very doable. So big thanks to Stephen for this. Really thrilled with the whole idea behind it. The writing's great and it gave us some chuckles, so certainly check it out. Now, the other thing I need to mention is some of our patrons have managed to get through the Star Wars Sudoku hunt. So very well done to Tobias Binder or Binder, to Joe Parle, to Brendan Wright. Now, Brendan, you did, I think, have a typo in your answer, but I've given you credit. David Rensberg, Michael Straneri, Tanner Bartichak, I might be saying that wrong, I'm really sorry if so, and Alex, Amanda, and baby Elliot Ratzloff. Now, that was a lovely story. Alex's email said that basically once they get their new baby down, they put the puzzles on the big screen and work on them together. So Alex and Amanda, that's above and beyond the call. Although, Alex, you have made me say Alexa, and therefore Alexa has turned herself on to join in the video. Apologies. She is very keen, I think, to get in on Cracking the Cryptic stuff. Anyway, that's all I've got to mention. Let's get on with the puzzle. Here are the rules. Normal Sudoku rules apply. Digits along an arrow must sum to the digit in that arrow's circle. In cages, digits must sum to the small clue in the top left corner of the cage. Okay, all right, all our cages are in the same boxes of the Sudoku, so we don't need a rule about digits not being able to repeat within cages, because they simply can't due to the rules of Sudoku itself. Along the indicated main diagonal, so just on this diagonal, marked in blue, the digits cannot repeat. So those outline cells there have to be a set of the digits 1 to 9 once each. Inequality signs between 2 cells point to the lower of the digits in those cells. So we're told that this digit here is lower than this digit here. And the same is true here. This digit is lower than this digit. And that's it. Do have a go. The way to play, of course, is to click the link under the video as usual. Now I get to play. Let's get cracking. Now, I mean, these arrows in the corner are a little bit interesting, perhaps. Although, not as interesting as some puzzles I've seen. I've seen puzzles before where you can prove that all 4 of these digits have to be different. And often, I think Tall Cat's done a series like this where they all have to be at least 6. Now here, that's not true, look. The minimum those 4 digits can add up to, and the same seems to be true, it's asking the same question in all 4 of the boxes. The minimum those 4 digits can add up to would be 1 plus 2 plus 3 plus 4. Well, that's 10. But so 10 divided by 2, because obviously these 4 cells, well, each sum has to be taken individually, means that each of these circles must be at least a 5. And I don't know that we can do better than that. Well, let's put that in case it's interesting. 5, 6, 7, 8, 9 into the circles in the corners. An 11 cage, we can actually just write in the digits for that. That must be 1, 2, 3 and 5 in 4 cells. Now we've got an inequality sign here, so that's not a 1 and that's not a 5 as a result of the inequality sign. There must be a 1 in a 4 cell 13 cage. You can try and do it with 2, 3, 4 and 5 as much as you like, but you'll only get to 14. And I suppose there must be a 9 in a 27 cage for similar reasons, but the other way round. So if you don't have one, you'd have 8, 7, 6 and 5 as a maximum, and that only adds up to 26. Right. Okay. I'm running out of ideas now. I've only got one idea left, so I hope that that proves fruitful. The idea I've got left is to look at these perimeter squares. Yeah, I mean, it strikes me as interesting that these 2x2s here add up to a great big total, and these 2x2s here add up to quite a little total. So I think we're looking at some more set stuff here, aren't we? Some set equivalence theory. So if we highlight row 1 and row 9 in one colour, and column 1 and column 9 in another colour, in a different colour, we can, yeah, okay, there's at least something we need to explore. So what am I doing here? What I'm doing is I'm making use of the geometry of the Sudoku grid. So firstly, let's look at the blue cells I've highlighted. Now those 18 cells, we don't know what the digits, well, we don't know how the digits within these rows are disposed yet. Hopefully one day we will, but we do know exactly what digits they are, because this is a complete row of the Sudoku and this is a complete row of the Sudoku. So those 18 digits I've highlighted in blue are 2 sets of the digits 1 to 9. They will be comprised of 2-digit 1s, 2-digit 2s, 2-digit 3s, etc., all the way up to 2-digit 9s. Now the same is true, of course, for the orange cells, because this time I've just highlighted 2 complete columns of the grid. So that will be that the orange cells are comprised of 2-digit 1s, 2-digit 2s, 2-digit 3s, all the way up to 2-digit 9s as well. So at this point, before we do any meddling with this, we can say that the orange cells and the blue cells are exactly identical in total. They have the same composition as a set. But look, this digit, whatever it is in the finished grid, it's in the orange set and it's in the blue set. So if I remove it from the orange set and the blue set, it's still true to say at this point that the orange set and the blue sets must be the same digits still, because they were the same digits before, and I've just taken exactly the same digit, whatever that digit is, I've just taken it out of both sets. So the sets are still the same. Same is true obviously of all cells in the puzzle that have both colours in them. But look, I think the trick here is going to be to look at these arrows. So now, at this point, we've got to be a bit careful about this. But at this point, we know that the blue set of digits and the orange set of digits are still the same. They therefore sum to the same total. Now, whatever those 2 digits sum to is the same as whatever those 2 digits sum to. So if I take those cells out of blue and these cells out of orange, I am removing the same total from both sets. And therefore, having done that, I can say that it's still true to say that the blue sets, the blue cells remaining and the orange cells remaining still add up to the same total. Note they don't anymore have to be the same digits, because obviously, I mean, let's imagine this was a 6 and this was a, I don't know, a 2 and a 4, and that was a 1 and a 5. I clearly haven't taken the same digits out of both sets. I took a 2 and a 4 out of blue, and I took a 1 and a 5 out of orange. But in total, obviously I've taken cells totaling 6 out of blue and cells totaling 6 out of orange. So it's still true to say that the remaining blue cells and the remaining orange cells add to the same number. And I can repeat that trick, look, around the grid. These must have the same sum. Those must have the same sum because they're adding up to the same circle. The same is true here. So now we're getting to a point where it might get interesting, because now we know that the remaining orange cells add up to the same number as the remaining blue cells. But here I suspect that these 2 by 2s are going to be rather, they're putting opposite pressures on their digits, so that the 2 big cages here are forcing the blue cells to be low, because if these cells are too big, we'll break the total for the box. Remember, any box of a Sudoku, because of the secret, and the secret is something I only tell my favourite people, but today that includes you. Now, any box of a Sudoku, indeed any row or any complete column of a Sudoku, will contain the digits 1 to 9 once each. So I know that that box adds up to 45, because that's what the sum of the digits 1 to 9 is. So I can't have too high a total in these blue cells, otherwise the whole box will add up to more than 45. But the orange cells work the opposite way, look. The orange cells can't be too low, because if they're too low, these cells would have to be greater than their maximum possible value in order to ensure that the box added up to 45. So we have opposite pressures acting on blue and orange, and hopefully they will meet some equilibrium in the middle, which means we know what they are. So how are we going to do this? Let's maximize those digits out. So if those digits and those digits were maximized, then we would know the sum of orange. Okay, so let's do that. So we've got 11 plus 13, that's 24, plus 2 lots of 17 is 34, so that's 58, which means that, but we know that 2 whole boxes of a Sudoku add up to 90, so the orange cells have to be 32 or greater. That's forced. If we reduce any of these 9/8 by anything, we will force the oranges above the value of 32. So we can take those 9s and 8s out. We've got no idea what these digits are yet, but we do know that orange must be at least 32. And therefore, blue must be at least 32. Now, if we put the opposite, if we put 1s and 2s into these squares, let's do the same thing. So then we've got 27 plus 24 is 51, plus 6 is 57. Ah, you rotten thing. It's not quite right, is it? So the blue cells have to be 33 or lower. That's annoying. So we've reached a point where we've worked out the orange cells have to be 32 or higher, and the blue cells have to be 33 or lower. So we know that either orange and blue add up to 32, or they add up to 33, but we don't know which one is true. And that is rather annoying indeed. We're clearly on the right lines though, aren't we? We just don't actually we haven't reached equilibrium. The universe isn't quite in order yet. And she hasn't started to sing to us. So, okay, well we can do some simple deductions therefore, because, yeah, so in order to look at the maximum values for these dominoes, I used 9s and 8s. There's 1 degree of freedom here, isn't there? Either these are 9s and 8s, and that's one possibility, or we can reduce one of those digits by exactly 1. So these cells either add up to 34 in total, or they add up to 33 in total. There is no more leeway than that. So there must be a 9 in both of these dominoes, and they are made up of either a 7-9 and an 8-9, or 2 lots of 8-9. And the same must be true of these squares. So there's definitely 1s in them, and they're either 1-2 pairs, or one of them is a 1-3 pair. Okay, so now we are going to do what exactly? Don't know. I don't know. Let me just stare at this. Sorry, I'm not actually spotting what I need to do here. There has to be a 1 in one of those 3 squares, and there has to be a 9 in one of these 3 squares. It's not. Is it the diagonal somehow? Not sure that it is actually. Oh, how annoying. Oh, how annoying. Or is it this 11 cage? We must... Yeah, okay, we must have a 1 in one of those 4 cells. So there must be a 1 on one of these arrows in column 1. And the same is true in column 9, look, because we know that there's a 1 in the 13 cage. Ooh! Wow, okay, well that is a rare fish. Wow. Okay. Is that right? Hang on a minute. Let me just think about it. Yes, it is right. Wow. Okay. Now I'm going to show you something quite weird. Okay, I'm going to highlight some cells here. Those cells. And I'm going to allege that means I can write a 1 in the middle of the grid, I think. How do I do that? You may well ask. Right. So if we look at column 1, the 1s can go in the yellow cells only. If we look at column 4, the 1s must go in the yellow cells only. Look at column 6, the 1s must go in the yellow cells only. And if we look at column 9, the 1s must go in the yellow cells only. So, within the yellow cells that I've put in the grid, how many 1s are we going to find in the finished solution? Well, there's going to be 1 in this column, 1 in this column, 1 in this column, and 1 in those squares. So there are exactly 4 1s. But now I'm going to ask a facetious question, but it's important. Now I want to look at some rows of the grid instead. I want to look at row 2, row 3, row 7 and row 8. How many 1s are we anticipating there being in those 4 rows in total? Well, because of the rules of Sudoku, there's going to be 1 1 exactly in each row. So within those rows, within these cells here, there are exactly 4 1s. Because if we put 5 1s in, there must be a repeated 1. There are only 4 rows there in those highlighted cells. So now let's sort of juxtapose those things. We know that in the rows there are 4 1s, but we know also that the yellow squares contain exactly 4 1s. So we can immediately say that there cannot be 1s, there can't be any more 1s in these rows, in any of these cells. Because if there was a 1 in any of those green cells, then there would axiomatically now be more than 4 1s in those rows, and that will break the puzzle. But look, now I can ask where the 1s go on this funny diagonal that we've got. And I think this might be the point. Where does the 1 now go on this diagonal? It can't go in a green cell. It can't go in a corner. So it must be in one of those 3 cells in the central box, which means it must be there. That is a 1, which is rather beautiful. And that means that's not a 1, and these aren't 1s. And that pattern, by the way, is called a jellyfish because, well, not for any reason other than that's what it's called, but it involves 4 different rows and columns of the Sudoku. It's a very unusual fish. So the sort of order that you go in is an X-wing, which would just involve 2 rows and 2 columns, a swordfish, 3 rows and 3 columns, and a jellyfish, 4 rows and 4 columns. Anything larger, I think, is called a squirm bag, but can be sort of rearranged in another direction. So it's a very strange thing indeed. Okay, so this one's done nothing. I think it's done absolutely nothing. Oh no, it hasn't. Of course, there we go. I'm forgetting inequality signs. Look, now there's a 1 in one of those squares. Well, it definitely can't be on this inequality sign, because it would be implying 1 is greater than a digit that must be greater than 1 in this cell. So this is a 1. Okay, you can't put 1s in green. This is really weird, because actually I don't know that this is doing me any good at all. I'm so sorry if I'm missing something obvious here. It's just really peculiar. This is such a beautiful, it's a beautiful thing to find in your puzzle. And it's, well, I think it's been clearly set up by Samantha, but I don't really understand how to use it. No, the inequality sign here is fine. If this is a 1, that would be a very natural place for it to be. Alright, let's try and do the same thing with 9s then, maybe, because 9s... Oh, yes, in fact, 9s are easier. 9s are easier. Look at column 1 and ask where 9 goes. Well, 9 can't go on an arrow, because if it goes on an arrow, the circle would add up to at least 10. Even if you put 9 and 1 on the arrow, you've got to a double-digit number. So 9 is in one of 2 places in column 1, both of which see that square because of the magic of the diagonal look. If the 9 is here, it sees that square on the diagonal. If the 9's here, it sees that square by Sudoku. So that's not a 9 anymore. Oh, okay, I've overcomplicated this puzzle, but I don't care. I still think that 1 was very pretty. Now where does 1 go in column 9? It can't go on an arrow, and it can't go there because the 9 is definitely in this domino. It's no longer here because of the magic over in the red cells, so 9 must go there. And in placing a 9 here, it's not in that red cell anymore. That loses its redness, and this one becomes a 9. We've got 2 digits in the grid to go with our 2 1s in the grid. Okay. So now there's a 9 in my 24 cage, look. Okay, the 9 in my 24 cage. What else is in my 24 cage? Whatever I put in that square is also in my 24 cage. Yeah, okay. Hang on a moment. 1, 2. Is that logic good? I've got 1, 2, 3 and 5 in this 11 cage, which I have to put in this column somewhere. How could these digits go on arrows? They can't. You can't make these arrow cells add up to 11, because if they do, that would imply this square is a 2, which it clearly cannot be. So one of these digits at least must go in a circle, and it can only be the 5. So that, I'm arguing, is a 5. Yeah, this is what I like about Samantha's puzzles. He just has a brain that sees things in a slightly different way to a normal people, I think. It's really cool, because now I can look at 4. Where does 4 go in that box? Well, it must be there. So this 5 arrow must not be 1, 4 in this direction. That must be 2, 3. That must be 1, 4. Now in this column, where does the 1 go? Well, it's not in those squares, so it must be on the 9 arrow. So that's a 1, 8 pair. Oh, and now, right, and now the 8 bounces back into this domino in box 4. That can no longer have a 7 on it. So this is 8, 9. These squares are now known. They've got to be 4, 6, and 7 by Sudoku. Okay, yeah, and now my 24 cage suddenly acquires some potency, because it's now not only got a 9 in it, it's got a 4 and a 5 in it. Now 4, 5 and 9 add up to 18, so it must have a 6 in it as well. And then we can just ask where 6 goes in this row, and that must be on that arrow. So that's a 3, 6 arrow now. And these squares, now that's interesting, because now this domino is not a 1, 2 pair. It's got to be a 1, 3 pair, because I've got to put 3 in this box somewhere. It's going to have to be there. So that's used up our degree of freedom. So everything else, well, that therefore must be a 1, 2 pair, because we can't have losses of 2 degrees of freedom. And that means those two had to be maxed out, didn't they? Because, yeah, we were either looking at 32s or 33s. We needed one thing to adjust to take us in one direction. We now know that the adjustment is happening on the low side, so we need to max these two out. So that is therefore, whoopsie, sorry, so this is now 8, 9, this is 8, 9, there's an 8, 9 pair in the central box. We now know what these squares are. They are 2, 7 and 8. I suppose that's on that diagonal, so that's not a 5 anymore. Up here, this is 6, 7 or 8 now. Okay. I feel like I should be able to do something with this knowledge, but I haven't actually figured out how to do it yet. So what else do we now know about the state of the world? 2, 7, 8. These squares. So these blue squares add up to 15, don't they? Because the whole box adds to 45. We've got 27 plus 3 is 30, so they must add up to 15. These squares, yes, and we're going to get this by maths. Lovely. Okay, so this is 15. Those 3 squares there add up to 2 times 9, because the arrows will add up to 9. That is 9, so that's 18 altogether. 18 and 15 is 33. So these squares add up to 12, but we know that those squares add up to the same as that. So if they add up to x, this is also x. So 2x equals 12, x equals 6. Lovely. So these cells, therefore, are 1, 5 and 2, 4 in some order. Don't know if we know that order yet, but that is indeed what they are. Okay. So now, do we repeat that trick there? I'm not sure if we can. 13, so these add up to 15 as well. Oh, okay, that's not surprising because we've got 9s down here, so we must have a 6 at the top. So no, that's unhelpful. Okay, so I think we're gonna have to think harder now about how we learn what this is. Oh, okay. So whether this is a 4 or a 5, it's got to live in the 27 cage, because it can't go in those digits and it can't go in those digits. So if there was a 4 in here, then it would be 4, 6, 8, 9. Oh, that doesn't work. Yeah, oh, I see. No, the way to do this is different. The way to do this is to think about where 8 goes in row 1, because it's not on this arrow anymore, and it doesn't seem to be in those 3 squares. So it must be in these 3 squares. Now, if you can't put an 8 in a 27 cage, surely you've got to have loads of high digits with it. It's got to be 9, 5, 6, 7. That's the only way of doing it. Lovely. So that's 5, 6, 7, 9. These squares are now known. They have got to be 3, 4 and 8, adding up to 15, which is what we're expecting. Now this is not 2, 4 therefore, so that's not 1, 5. That 9 arrow is now not 3, 6, 2, 7 or 4, 5, so that's 1, 8. These squares are now 3, 5 and 7 by Sudoku, so those squares are 2, 4 and 6 by Sudoku. Oh, that's weird. So that square's not really helpful at all. Yeah, I suppose all that did was it positioned the 1. Oh, the 1 is useful. Okay, so 1, 5 go in. 5 must be in this domino by Sudoku. This must be a 2, 7 pair, again by Sudoku. Now we're just left with, well, we're left with these 2 arrows. Okay, I can see this can't be a 6. Because if this was a 6, this would have to be at least a 7. It can't be an 8 or a 9, and if it's a 7, that would have to be a 1, which it can't be. So that's not a 6. Now if that's a 4, there's no real pressure on it then. It could be 5, 6 or 7. Yeah, okay. Although is there actually, let me just think about that. If that's a 4, this can't be a 1. So it has to be a 2 or a 3. It would have to be a 2, and this would have to be a 6. Oh, that might be possible. I don't know. Sorry. I was just doing a brief excursion to see whether or not I could get this digit, but I'm not sure that I can. Let's look instead at maybe the diagonal. We've got to put 2 on it somewhere. Look, we've got 2's off the diagonal. Yes, 2. Where does 2 go on this diagonal? Can't go here because there's a 1, 2 pair, so it must go there. Which means that's not a 2. And those are not 2's anymore. And we can do exactly the same with 4. Look, 4 is not on this diagonal in the sort of periphery boxes, so it must be here. So that's a 4. We can take 4 out of these squares, 4 out of that square, 4 out of this square. Aha! And 4 out of that square, making this square a 2 now, and giving us a 4, 6 pair there, making this a 7, this a 6, and this a 4. Oh, come on, keep going now. This would be lovely if this finishes with some sort of alacrity from here. How do we get this done? Is it this now? So, okay, this wasn't 4, because I looked at that, didn't I? So this is now 2. Oh. Okay. I can see that can't be 3. So from a box perspective, this square here has to be a 5, 6, or 7. This it can't be 5, because this can't be 3. There's already a 3 in the box. If it's 6, that's a 4, which looks possible maybe. If it's a 7, oh, that's a 5, and that's possible as well. Bobbins. Oh no, hang on. But if in doubt, and this is classic me, always think about Sudoku. There's a 6 there. So that is in fact a 7. That's a 5. Those aren't 5s anymore. That's not a 7 anymore, I suppose. So this square is a 3 or a 5, just by Sudoku in this row. 7, oh, 7 comes out of there, so that's become an 8. So that square at the top is not an 8 anymore. Those squares are not 7s anymore. 1, 3, that's got to be a 4. That 8 is giving me the 9 and the 8 in the column. That's a 5, 6 pair here. So these squares here are a 7, 9 pair. We can take 9s out of these squares. We've got the 2, 7 at the bottom sorted out. Can we? Oh, and the 8 here also does the top. This is lovely. 8 and 3. So 3 is not in that circle. 3 must be in one of 2 places in box 5. And I think we're just looking for 5s, 6s, and so that square is a 5 or a 6 by Sudoku, and that's impacting this little square. Look, so that can't be 5 because that would require a 1 here, which it cannot be. So now I've got a 1, 3 pair here. So this is a 2, 5 pair. That gives me a 3 over here, a 5 here, a 7 here. So 3 in the central box now must go here. This is a 5 or a 6. There's probably some way we can work out which it is. Let's think about this. So if that's 5, this square here would have to be a 1 and that would have to be a 4, because we couldn't do 3 and 2 because there's already a 2 in that box. So we'd have to put 4. If this is 5, that has to be 4. If this is 6, you have to go 1 and then a 5 here, which looks possible actually. Oh, so this was never this is just never a 3. There's no way that this is ever a 3. It just can't be a 3. Either it goes 5, 1, 4, or it goes 6, 1, 5. So that's always 1, that's always 3, that's a 5, and that's a 2. So that's the reason for that inequality. We've now got a 1, 4 here, which bounces back up here, makes this a 6, makes this a 5, makes this a 9. That must be a 5 by Sudoku. That should be a 4, 6 pair looking upwards. Doesn't seem to be resolved, but that's still a nice find. Now we've got a 5, 6 over here. We must have a 3 there by Sudoku. Those squares have got to be a 4 and a 6, I think, to complete the box. Right, how's all this getting unwound? The 6 must be, I was wondering about that. 6 and 4, 4 and 2, 2 and 1, 1 and 8. So over here, there must be an 8 in this domino. Can we do the diagonal? Maybe not. So these squares are 7s, 8s and 9s. And these squares are 7s, 9s and 3s. Surely we know more about 3s than the puzzle's letting on. 2 here, yeah, we can keep going though. 2s and 7s go into the grid. There's got to be a 7 in this domino. So these are 7s, 8s and 9s. These are 6, 8s and 9s. We can get rid of 6 there. Yeah, so look along this diagonal now. There is a 7, 8, 9 triple, which makes that square have to be a 3. That 3 is lovely. It gives me a 3 and a 6, 6 and a 4. Oh, so this square is a 7, 8. That's not 8 because we've got an 8 here. So this is 7 or 9. Oh, and this 9 is giving us an 8 here. Sorry, I was just wondering what on earth was going on. But 7, 9 means this is a 6. The 8 on the diagonal means we can come up there and we find a 7, 9 pair. So that's going to be 8. That's giving us an 8 and a 9 and a 7 and a 7 and a 9. And the 8 is giving us an 8 and a 1 and a 1 and a 3 and a 3 and a 2 and a 2 and a 4 and a 4 and a 6. Oh, and I was just looking at, I'm looking at 2 things. Let's do the 8, 9 there, but let's look at this. It looks like it might be a deadly pattern and we wouldn't know the order of the 7s and 9s, but the diagonal is going to help us. There's a 9 already on the diagonal, so we must go that way round, and I think that is the puzzle finished. Beautiful. Absolutely beautiful. That is a real quality puzzle. And I'm now wondering whether or not that 1 in the middle, which was a hard 1-1 involving a jellyfish, was in fact a complete red herring of a sea creature of a different sort. Because I'm not sure how... I learned that this was a 1 from it, and that did come into play a bit later, but it almost didn't seem necessary. I look forward to your comments on that. I thought that puzzle was gorgeous though. Just, a lot about it and a lot of thinking and some really elegant logic around these 2x2 boxes and a little bit of set equivalence theory too. So I look forward to the comments, as I say. Thanks for watching, and we'll be back later with another edition of Cracking the Cryptic.